All right, net force. Have you ever heard of someone saying like your net income or something like that, net whatever?
Yeah.
What does that mean?
The sum.
All right, it means the sum. So net force is the sum of all forces acting on an object. Okay? Sum of all the forces acting on an object. So what do we know about force? Well, we know that it is a push or a pull. And we also have a formula for force. All right, that formula, F equals ma, is actually supposed to be F net equals ma, mass times acceleration. Okay? Now, the sum. The sum means you need to do what? It means you need to add. You need to get the total. So the total of all of the forces acting on an object. Emphasize an. We're talking about just one single object. Okay, this is not Newton's third law. Do not let's confuse with Newton's third law when you're having two objects acting on each other. This is net force. We're talking about a single object. Okay? Well, when we want to consider all of the forces acting on a single object, we often will draw a free body diagram to help explain and describe and visualize those forces acting on the object. So go ahead and glue that in, free body diagram. Okay? In this class, we pretty much focus on two dimensions. We avoid the third because it gets extra complicated with the math. But this is a free body diagram. The box in the middle represents any object. All right, so this drawing free body diagrams requires no artistic skills. Any object, whatever it is, we draw it as a box. And then we draw arrows coming off of that box. Notice all those arrows point away as if all forces were pulling on that box. And each one of those forces is represented by an arrow. Okay? Now, we have four different types of forces mentioned here. I'm going to start off with the F grav. All right? Force of gravity is actually called weight. All right? Your weight is actually a force because gravity is pulling your mass downward. Okay? So it always points down. The force of gravity or the force of weight always points down. Now, applied force. Applied force is the force that is, well, applied to the object. It's added onto the object. This is usually the push, the pull of something else going on. So whether it's the motor or the engine pushing it forward or something like that. Okay? So it's the force applied, which is what's causing the motion of the object. Force of friction. All right? Friction is always opposite the motion. So if I am moving to the right, friction is pulling me to the left. Okay? So force of friction is always opposite the motion. So this object, I can tell just by the fact that the friction is pointing to the left, this object must be moving to the right. Okay? The force of friction is always opposite the motion. Think about driving in a car. Have you ever rolled down the window and stuck your hand out? All right? And felt the wind? Okay? I like to call it roller coaster, playing roller coaster with your hand out the window. Okay? Now, have you ever noticed that if you're going like 35 miles an hour, 45, it's not very much fun? Because you feel the wind, but it doesn't really like have much, to like raise your hand up. But if you're going like 55, kind of becomes fun. Get up to like 70, it's like woohoo! You can play like this really awesome roller coaster game with your hand. All you have to do is like bend your fingers back and your whole hand goes up. And bend your fingers down, your whole hand moves down. Just moves your whole arm. don't do it above 70 miles an hour, because if you do, a little flick of the finger and your whole arm goes flying backwards and you hit it on the back of the window and it kind of hurts. So, don't do that. Yeah, I've done that one. So, that friction is air resistance. That's the air pushing against your car. You're going one direction, but it pushes you the opposite direction. The faster you're moving, the stronger that force of friction is. Okay? And that's just air resistance friction. There's also friction with like the tires against the street and all sorts of other friction going on. Okay? But that friction is always going to be the opposite of the motion, because friction opposes motion. Okay, so with the free body diagram, we've got the force of gravity, applied force, and the force of friction. For normal force, okay? Normal force is that idea if you're standing on the ground, Newton's third law, you're standing on the ground, your weight's pushing down on the ground's pushing back up on you, all right? That is the idea of the ground pushing up. That's your normal force, okay? Unless you're free falling, this is like falling out of an falling out of an airplane or something, most likely there's a normal force happening, all right? And that normal force, unless you're moving up or down, that normal force and the force of gravity are actually going to be balanced out, okay? So they're often ignored because they balance each other out. That normal force and that force of gravity are going to be the same, okay? So that's a free body diagram, so you have an idea of what's going on there. Now take these two papers, fold them on the solid line. Okay, fold on the solid line, these two papers. Okay, we're going to first look at the one that has the dog sled. Okay, so if forces are going in the same direction, we add them. So we've got 3 dogs here. Each dog is pulling the sled forward with 5 newtons of force. Okay? So we have 5 newtons of force by each dog pushing the sled forward, pulling the sled forward. All right, now if you notice the guy that's running the team here in the back, his foot's sticking out there, he actually pushes as well. And we're going to say he also pushes with 5 newtons of force. Okay? So he's pushing, they're pulling. It doesn't really matter if they're pushing or pulling. They're all going the same direction. And because they're all going the same direction, we just add them up. So if I want to know the net force, I need to do 5 plus 5 plus 5 plus 5. All right? So add them up. My net force is going to be what? 20. Now, what are my units of measure for force? Newtons. And force is a vector, which means it has direction. What direction is the sled moving? Right. All right, we're going to say to the right. Keep it easier. No compass necessary. To the right. Okay? So the net force, 20 newtons to the right. Okay? So go ahead and fold that closed and write on the front, forces in the same direction. All right, pretty easy. We just add them up. Okay? Now the other one. This is what happens. This is what we're going to talk about when forces are in opposite directions. Okay? Forces in opposing directions. Okay? Going in opposite directions. What do we do then? Well, we subtract. Okay? So we've got a box here. We've got 3 forces pushing on it. 5 newtons to the right, 3 newtons to the left, and 2 newtons pushing up. Okay? Let's pay attention. Now when we do this, we're going to simplify it. We're going to separate the vertical from the horizontal. So let's talk first about the horizontal. The horizontal forces acting on this box. We've got 5 newtons to the right, we've got 3 newtons to the left. Now, we've talked about direction before. If you're going to the right, it's positive. If we're going to the left, it's negative. All right? So, 5 newtons to the right. That's your positive. And you're going to do the sum, add a negative 3. So basically 5 minus 3. Does that make sense? So 5 minus 3 gives us 2 newtons. All right? And what direction would that be? Right. To the right. So that 5 and that 3, that 3 kind of cancels out part of that 5, and the net force horizontally is 2 newtons to the right. Okay? Vertically. All right? Up is positive, down is negative. So we've got 2 newtons going up. Do we have anything coming down? No. Nope. So no force is coming down. So our net force vertically is 2 newtons up. All right, so go ahead and take that one. Take those 2 papers. We're going to glue them in right there on that page. That'll be the last thing we put on that page, so don't worry too much about the spacing. All right, just put yourself a little note here. Force is a vector. It has direction. Hence all of the arrows pointing in those different directions. Force has direction. All right, now we are going to go to the oops page. So don't turn the page. Just transfer over there to the side. Here we go. Oops page. On our oops page, you are going to write at the top, the net force acting on an object determines the object's motion. Okay, so we've talked about motion before. And I always say, describe the motion of the object. Describe the motion. Well, there's not many options when it comes to describing the motion. All right? It's either at rest, moving with a constant velocity, accelerating, or decelerating. When we basically come down to it, there's those 4 options. Okay? And all of that is determined by the net force on the object. So, let's talk about balance forces. All right? These 2 papers look very, very similar. Make sure you find the one that says balance, not unbalanced. We want the one that says balance forces. Glue that one in first to the left. Okay. Balance forces. When all the forces are balanced, that means I've got, for example here, I've got 3 newtons of normal force and I've got 3 newtons of gravitational force or weight. I've got 5 newtons of applied force to the right and I've got 5 newtons of friction to the left. For every force going up, I've got 1 balance it going down. And for every force to the one side, I've got to balance out with a force to the other side. Okay? All of those forces balance out. Because those are all going opposite, you subtract them, you end up with a net force equal to, we've got 3 going up and 3 going down, 5 going to the right, 5 going to the left. What's my net force going to be? 0. All right. When I have a net force is equal to 0. All right? They all balance each other out. When that happens, we say that it is in equilibrium. Okay? We describe that as being in a state of equilibrium. Okay? All of the forces are balanced. It's in equilibrium. Now, if an object is in equilibrium, there are 2 different motions it can have. All right? The motion of the object is either going to be at rest or at a constant velocity. Now, let me explain in a few examples. So, imagine an object at rest. Pretty typical object at rest. All right, this you don't have to draw if you don't want to. I'm just drawing it in here for the sake of drawing it in. A flower vase. Usually something that stays pretty still, right? So, we're going to draw a free body diagram for the flower vase. We're going to say it has a weight of 2 newtons. Okay? The normal force, the force of the table pushing up on that flower vase is also 2 newtons. Okay? There's no forces pushing it to the right, to the left, or any other direction. It just has weight and normal force acting on it. That vase is at equilibrium. All right? It is also at rest. Do we agree? Yeah. All right. At rest. Now, another option. You're driving in your car. We have a car. No, I'm not an artist. Okay? The car. All right? It's moving forward. Okay? It's got the engine applying a force to move it forward. It has wind resistance pushing it backwards. All right? It's got its weight pushing it down, and it's got normal force pushing it up. So, we're going to draw the free body diagram for that. Let's start off, make it easy. Let's do the weight first. We'll say this is we'll say it's a really light car. We got 100 newtons. Okay? Going down, that's its weight. Normal force is going to be 100 newtons going up. Those two balance each other out. Now, this person is pushing on the gas pedal just right, applying just enough force of engine so that the speedometer does not move. Okay? So, we've got that applied force of the engine, pushing it forward, we'll say 80 newtons. If you were to put your hand out the window, you would feel the wind blowing against your hand, right? We have 80 newtons of wind resistance and friction happening. In that situation, the car is moving at a constant velocity. Okay? Because that force pushing it forward balances against the force of the wind pushing it backwards. Okay? A similar scenario would be out in outer space. The baseball in outer space. I throw it. All right? As soon as it has left my hand, it has a velocity. And it's going to maintain that velocity, a constant velocity. It's not going to speed up, it's not going to slow down because there's no forces acting on it. The free body diagram for that baseball flying through space is nothing. It's just a box. There are no forces acting on it. There's no gravity, there's no wind resistance, because there's no air in outer space, okay? Because we have no forces acting on it, our free body diagram has no arrows. That ball is going to move with constant velocity. Okay? Does that make sense? Yeah. Guys, remember the air hockey puck, right? Yep. There's no forces acting on it. There's no friction. After I kicked it, it's not like I was still pushing on it. Okay, but it was moving with a constant velocity. All right, goes right back to that inertia. An object in motion wants to stay in motion at a constant velocity. All right, I'm going to put a little squiggly line right there. What if the forces are unbalanced? What if they don't cancel each other out? What if we're not at equilibrium? Well, let's talk about that. Last piece of paper. Glue it in below there to the left. If we have unbalanced forces, the net force is not going to be 0. Okay? It's anything but 0. It can be positive, it can be negative, but it's not 0. So the net force is not 0. In that situation, we have an unbalanced forces. So look at our example here. We've got 3 newtons of weight going down. We've got 3 newtons of normal force going up. We've got 5 newtons of friction to the left. And we've got nothing to the right. Okay? So it's not balanced. We have a net force of 5 newtons to the left. When we have these unbalanced forces, the motion of the object is going to be accelerating or decelerating. The object is either going to be accelerating or decelerating. So, let me give you an example. Let's go back to the car example again. Okay? Let's say you've been going at a constant velocity and suddenly you take your foot off the gas. All right? We call that coasting. All right? You're already moving, but you take your foot off the gas. Okay? If you were coasting, what are the forces acting on the car? Well, we still have the 100 newtons of friction, of weight going down. We still have 100 newtons of normal force. Do we have an applied force from the engine? No. I've taken my foot off the gas. The engine isn't pushing the car forward anymore. All right? It's moving because it has momentum. Another topic, next topic after Newton's laws. Okay? But we have that coasting. What's really going on here, we still have the air resistance, right? You still have the wind blowing in your face. You're still going like 50 miles an hour, right? So we still have the friction. Now, as you slow down, that friction is going to decrease, but there's still going to be friction until it comes to a stop. Does that make sense? So that idea of coasting, we have that this one is going to, because this is the friction, this is going to decelerate. If you take your foot off the gas, what happens? You slow down, right? What's happening is the wind is actually pushing against you, bringing you to a stop. Okay? What about accelerating? All right. So accelerating, we'll stick with the car again. All right, this time we're making a sports car. Put a little spoiler on it. Okay. Our little sports car with a spoiler on it. Now, this time he's going the light, so he's standing at the stoplight. Okay? The light turns green. Green. Yay! Go! And he takes off, okay? The forces acting on that car. We still have the weight. We still have the normal force. However, we now have, if you hit the gas really hard, all right, let's give it 110 newtons from the engine. But because you're just taking off, you're going really slow, right? If you're going really slow, the wind friction, that wind resistance, is very small. So that is a very small resistance due to friction. In this situation, what happens? You accelerate. All right? You go faster and 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 faster. Okay? And as you go faster and faster, this friction is going to get bigger and bigger and bigger and bigger and bigger. Eventually, those two will be balanced out, and that's when you reach a constant velocity. Okay? Making sense? So, this idea of net force actually brings together the law of inertia and Newton's second law. All right? So, first law of motion, backing up here. First law of motion, an object at rest wants to stay at rest. At rest, its forces are at equilibrium. They're balanced out. Object in motion wants to stay in motion. Again, that constant velocity, it's at an equilibrium. The forces are balanced. So inertia is when the forces are balanced. You're either at rest or you're at a constant velocity. But what if the force is not equal to 0? If the force is not equal to 0, then we apply Newton's second law. And we multiply, we use mass, and we can figure out the acceleration. Okay? So we get that relationship of the force, the mass, and the acceleration. Remember, if there is a force, if there is a net force, we will have acceleration or deceleration. All right? If the net force is not equal to 0. So the idea of net force brings together both Newton's first and second laws into one concept. Does that make sense? So, how an object moves completely depends upon the forces that are acting on it.